So welcome everyone. This is another seminar in our data science seminar series for EC in RISE. And as you might have seen, the set of speakers that we have, we managed to invite our top level, and today is no exception. So we have with us Professor Mert Gürbüzbalaban from Rutgers University. So Mert is now a professor at Rutgers, but he spent some time at MIT in Leeds, working with Asu Ozdaglar and others in optimization. He holds a bachelor's degree in electrical engineering and mathematics from Boğaziçi University in Turkey, and a PhD degree in applied mathematics from the Quran Institute at NYU. Mert has won several awards, best paper awards in many conferences, and he is known for making fundamental contributions to optimization theory, specifically SGD, and also some things related to coordinated descent and randomized gradient descent type of things. That's the way I met Mert, but he has made other contributions in many other areas on signal processing, optimization, and control theory. So without further ado, thank you, Mert, for joining us today. And yeah, go ahead with your talk. Thank you.
Thank you, Cesar, for the generous introduction. And it's really a pleasure to be here. Thanks again to the organizers for inviting me. Currently, I'm not able to see the attendees, but feel free to jump in, if there are any questions. And so today I'll be talking about stochastic gradient descent methods with a focus on deep learning applications. And these methods work pretty well in practice. And so there's a lot of interest in understanding why they work, so that we can improve them. And today I will argue that stochastic gradient descent methods as optimization methods have particular structure in their particular noise structure, which will allow them to work better. So probably in this talk, I will be focusing on stochastic gradient descent methods and why do they work well on unseen data. In other words, why do they generalize well? And as Cesar mentioned, I also have work in, this is more like I would say more like a talk on statistics, but I also have work in distributed algorithms, Bayesian learning, robust learning, and some other contexts, and I will be happy to talk to you in person about that, separately. Okay, so just let me give you a quick introduction to stochastic optimization for deep learning. I think for many of you guys, this would be familiar, but just to have a quick introduction. So in stochastic optimization, we want to minimize the expectation of a random function. So the randomness comes from the data. So you can think that you have a predictive model where the model parameters are parameterized by the vector x. Z is your data. You want to fit your model to data. So f is like your loss function that characterizes the cost of misfit to data, or cost of prediction error, if you wish. And basically, you are trying to have some sort of average performance, meaning that you are trying to minimize the expectation to have the best model that can fit the random data. So if you choose your function to be a quadratic, you end up getting a linear regression problem. So if you end up choosing f more generally, you can be in the context of generalized linear regression, such as logistic regression. Or if you choose f to be a nonlinear model, you can be in the deep learning scenario. So today I will be focusing more on the deep learning kind of setup. Let me kind of give a quick introduction. So in deep learning, we are trying to classify or classify data, or do some sort of prediction. The simplest example is that you can think that you have some images. You can think them as 0, 1, some sort of input depending on the pixel value. You feed them to a network, and you want the network to output 1 if it is the digit 1. You want the network to output 2 if it's the digit 2, etc. So you want to classify basically images, right? Handwritten images. And the way it works is that this deep networks kind of mimic the brain structure. What they do is at every your model consists of layers. At every layer, you take a linear combination of the output of the previous layer with some weights. So these links give you some weights that you are trying to figure out. And after that, you add some sort of offset or bias to these values. If necessary, apply some nonlinearity and sort of go to the next layer. So you have this layered structure, and in this particular form, like your prediction is in the form of a composition, right? So basically, if you choose your F in the deep learning context, you are trying to figure out the weights and the bias vectors to be able to fit the data, right? So a lot of times, because we don't know the data distribution, right? So if you are trying to learn handwritten images, right, you may not know what is the distribution over the pixels, right? So you can say, well, a lot of times what we do is, instead of the expectation, which we don't have access to because we don't know the underlying data distribution, what we do is we replace the expectation with a finite average. So this way, essentially, this problem is known as empirical risk minimization. So you are trying to fit to the data that you have at hand. So in terms of optimization methods, what are some methods you can think about? So in practice, first of all, we may have a high dimension. So if you are thinking of some applications, a lot of times we may have millions or even billions of parameters, and we may have also a lot of data points. So if you want to sort of apply the most basic algorithm, optimization algorithm, gradient descent, one issue is that basically to compute the gradient of a sum, you would have to pass through the whole data set, because each function fi here is associated to a data point. Consequently, basically, the problem is that just to compute a gradient descent, computationally it would be very expensive. So gradient descent would sort of so the idea in stochastic gradient descent is to have a cheap stochastic estimate of the gradient, so that you can optimize this finite sum problem in a much cost-effective fashion in terms of per iteration cost. So I think probably I don't also need to motivate why we're interested in deep learning too much for this audience. But if I just want to kind of mention a few applications, so deep learning essentially leads to state-of-the-art performance in many computer vision tasks. So the simplest example would be, maybe these days there's motivation to develop self-driving cars, and a lot of startups that work on this imaging technology, where the cars have to sort of distinguish pedestrians from cars. So they would be doing things based on deep learning. So for computer vision tasks, this has been kind of very, very popular. In machine translation, if you want to translate between languages, or if you want to predict COVID, or if you want to predict any type of social media effect, a lot of times deep learning has led to sort of a kind of a state-of-the-art performance in many kind of prediction tasks. So that's why we are interested in deep learning and SGD, stochastic gradient descent, which is like a fundamental algorithm for this learning problem. So how does the stochastic gradient descent work? As I mentioned, you say, well, I'm going to pick a subset. I'm going to estimate the gradients randomly from a subset of points. So for instance, B is the bet size, so you choose a smaller number of points. Let's say if you have 1 million points, you choose maybe 100 points, right? B is your bet size of 100. And based on this average, you kind of replace the gradient with its stochastic estimate. So that's what the stochastic gradient is about. So in this talk, I am assuming that these estimates are unbiased. But in the past, I have also worked on some other schemes where the gradient estimates may not be maybe biased. So for instance, if you randomly select your points to estimate the gradients, you will be sort of in the unbiased scenario. So, okay. So as I mentioned, when you talk to industry people in data science, like people in Amazon, Netflix, Facebook, a lot of times you will see that they are using this method very, very frequently, and a lot of packages would have it implemented. So just let me give you the big picture of how these algorithms behave. Like in gradient descent, the idea is that basically you are going downhill. So essentially, if you think of this optimization function, it can be non-convex in deep learning, and you see that gradient descent follows this sort of this steepest descent direction. So this is well known. So what stochastic gradient descent does is that because of the noise in the gradients, you don't have to necessarily follow this path, right? So you sort of zigzag, and in this case, you see that, for instance, because of the noise, the iterus x1, x2 to x6, right? In this case, you see, for instance, stochastic gradient ended up converging to a different local minimum than what gradient descent converged to. So then the question you may ask is, okay, gradient descent and SGD, we expect them to converge to different points or different local minima. The question is, which one is better? Or what can we say about what type of minima SGD finds? This is motivated by the fact that even a simple algorithm like SGD can really achieve very high kind of prediction accuracy in many tasks. So we want to understand what's going on with SGD versus gradient descent. So as you know, like deep learning is a bit like an empirical field where people try a lot of algorithms on different data sets, and sometimes the results are a little bit may have a bit of conflicting nature, in the sense that in one data set, things work differently. In another data set, it may work differently. But one thing that's very commonly observed is that people have seen that if a local minimum is ending up in a wider valley, then it will be generalizing better. So for instance, in this picture, we have M1 and M2. M1 is like a sharp minima because it's lying in a very kind of sharp valley, whereas M2 is like lying in a more like a flat surface. So based on empirical experiments, people have found that gradient descent, a lot of times it finds like a sharp minima, whereas a stochastic gradient actually has tendency to converge to this flat minima. And people have seen that this type of local minima in the practice, in the test data set, when you develop your model and test it on the unseen data, a lot of time people have observed that flat minima has this nicer kind of generalization properties. And this is somehow, there's a little bit theory on this. There's a paper going back to 1997 by Hochreiter and Schmidt-Huber. There are some other theoretical papers which show this in particular context. But the overall agreement is that SGD prefers wide minima. And this is the question is, you can ask why it's the case. Why is it the case that SGD converges to a flat minima? So the talk that I will, so now the results that I will present now is going back to a paper back in 2019, 2 years ago, that we wrote with Umut and Levent. But more recently, we have a more comprehensive journal version that has more theoretical results in it. That's on archive and in revision. So let me tell you a little bit about these results. So the question we ask is, why would SGD prefer wide minima? So if you think about the difference between gradient and a stochastic gradient, right, the difference is only the noise in the gradients. So then you can say, well, let's try to understand this noise structure. So how does the noise look like? Well, remember, you choose random data points and then try to do some sort of average to estimate the gradient. So your actual gradient error, because of this, it is actually an average of IID random variables, because you kind of go and uniformly sample data and try to estimate gradients, right? So then your essentially kind of gradient error is nothing but an sort of average of IID random variables. So one thing you can say, well, analyzing discrete objects is very hard. So let me try to maybe sort of have some sort of continuous time model. For instance, if you want to understand gradient descent, you could sort of have a continuum model. For instance, there's a model called gradient flow. So the same thing here. People have thought about, okay, maybe we can try to model stochastic gradient and model the noise structure. So the natural assumption that you can have is that you can say, well, in the iterations, X iterate is random. So you don't know whether the gradients have finite variance. But let's say for the sake of simplicity, let's assume that all the variables you are averaging over has some finite variance. Then we have the classic central limit theorem that tells you that, oh, like average of random variables, if they have finite variance, should look like a Gaussian, right? So from here, you can say that, well, the noise should look like a Gaussian. And then you can say, well, what kind of model would be right if I want to study SGD? Well, if the noise is Gaussian, naturally, if you take the limit, you should find something like gradient descent in continuous time, right? Plus something like a Gaussian noise structure. So this is known as a stochastic differential equation. It's a differential equation, but it has some sort of a Brownian motion in it, which is like a Gaussian process. So in other words, if you are doing stochastic control, for instance, you would be working with this kind of processes all the time in the EC department. So essentially, this is a model, continuous time model that you could use to study SGD. And people said, okay, let's study this model, where, and then we know that this kind of models have an equilibrium distribution. So in other words, if you have gradient descent plus white noise or Gaussian noise type of thing, we know we have a formula for the equilibrium distribution of the iterates. And from this, people try to develop some insight. And there's a nice paper by Jastrzebski et al. From 2017, where they argue that essentially the time that SGD spans, so basically the width that we are talking about in terms of the width of the local minimum that SGD will prefer, the ratio step size over B, step size over bed size should be relevant. So based on this classic theory, we know that step size over bed size, if this quantity is large, SGD has a bit of higher chances of preferring a kind of wide minima, right? So this is nice, but so this existing theory had some limitations. So what are they? So the first of all, when you talk about the stationary distribution in these continuous time models, the problem is that you need to wait forever for the stationary distribution to kick in. So there are some results that we know. For instance, there are several papers by Maxim Raginsky, Sasha Raklin, and others. We know that this kind of continuous time models would require exponentially many iterations. Even this goes back to simulated annealing literature. So you know that you need exponentially many iterations to have this asymptotic region to kick in. So this is not realistic because let's say we may have millions of parameters, and so exponentially e to the 1 million is like more than the age of the universe. So that's very big, and that's not very realistic. So one question we asked, like maybe it's because if we apply momentum. So in other words, so you see this continuous time model, and imagine that there's a term we add that can sort of accelerate this dynamics, where we add some sort of a momentum term. So we look at accelerated versions, if you wish. If you do that, it turns out that you can converge to your equilibrium faster by a square root factor. So this is in the non-convex setting. So the convex setting of acceleration is well studied. So we can still show an acceleration in the non-convex setting by square root factor. But the problem is that square root of e to the d is still like e to the d. So in other words, the fact that you can add momentum doesn't really kind of help you too much. It's still very slow in terms of like behavior. Another problem is, so if you go with this continuous time model, So if you look at how much time you need to be able to jump from a local minima to another local minima, that will scale very badly, exponential in the height. So if two minima are separated by a height h, you need e to the h iterations. And like based on some data sets that we looked into, I mean, this doesn't also look too realistic. Like you can't actually compute the sort of like the risk surface very accurately. But when you look at some simple examples, you see that e to the height doesn't look very realistic. More importantly, so empirically speaking, when you just go and take a simple network and let's say look at the histogram of the noise, what you see is something interesting. So in the beginning, here you see the pictures. In the beginning, when you just do some batching and then you can have the histogram of the noise, right? So what you see is that in the beginning, the noise behaves a bit like Gaussian. But over time, when you do training, the noise becomes more like what we call heavy-tailed, meaning that the decay in the so you see there are big entries, and the decay in the noise is not like a Gaussian, but slower with occasional large values. So in other words, if you just try this, the Gaussian models have some issues. So then the question you may ask, like, what's going on? I mean, you have to have something Gaussian according to the theory, right? So it turns out that, I mean, in many practical problems, especially in, for instance, audio signal processing and other fields, in finance, for instance, we know that the data may have like fast fluctuations, so that your finite variance assumption may not hold. So in particular, if the gradients that you are working with does not have a finite variance, right? It turns out that when you average them, you don't find something Gaussian, but you find a more general distribution called the stable distribution. So let me give you an example. Here you see in yellow, you have the Gaussian distribution. If on the other hand, you have like a polynomial decay like this in your gradients, a bit slower decay, then if you average them out, then you find something else called an alpha stable random variable, where alpha is a variable. So for instance, when alpha is equal to 1.5, this distribution will be decaying slower than a Gaussian, right? So the more heavy tails you have in your gradients, when you average them, you will have a kind of a slower decaying distribution, in the sense that it's possible that, according to this theory, it's possible that the Gaussians may not arise. So then when we say, okay, we don't know why this heavy tail business is happening, but let's just check it on, we can just check it on real data, right? And so later on, I will show you a lot of experiments that show that this is indeed happening in different contexts. So just to give you, going back to our kind of continuous time modeling problem. So here in yellow, you see, for instance, the paths of the Brownian motion, where you see it's actually the yellow is the paths of the Gaussian noise, if you wish. So when you have this more heavy-tailed distributions, then the idea is then the limit, you can work out the limit, then the limit becomes like another continuous time model. But now the noise is not Brownian, but it's something else called the Levy motion. And Levy motion has this structure that allows it to have jumps. So for instance, if you look at the blue curve, as you can see, you have jumps. In other words, you're modeling SGD with some continuous time process that allows jumps in it. Okay, and so that's what we proposed, because the Gaussians didn't really reflect, as a model, didn't really reflect the practice, and it has some shortcomings in some scenarios, right? So then it turns out that this can correct some of the issues. So remember that I was talking about, if you want to move from one local minima to another one, you need exponentially many iterations. Now you need only polynomial in the height h. Why is this? Because this process actually allows jump in it. And in practice, a lot of times, if you just check out SGD in deep learning practice, you see that maybe the loss function comes like this, and then it jumps. And so SGD has this jumpy behavior essentially, a lot of times in practice, you see that, it jumps from value to value, and sort of this process is sort of modeling that. And in some sense, it's more realistic in the sense that you don't need to wait forever to be able to jump from one local minima to another one. Okay, so basically we have this model, and essentially, probably the actual noise is not maybe alpha. It is not maybe alpha stable, but at least on realistic data set, we have. So, for instance, in this picture, you see the real noise is like the blue one. So we see that the Gaussian is not a fit. So alpha stable, at least on this particular example, seems to be more realistic. But this doesn't necessarily mean that the noise is alpha stable, but it says that it can be used as a model. Okay, so one thing that I wanted to point out, so this is for optimal. So this discussion is related to simulated annealing algorithms in actually optimization. So for non-convex optimization, remember this continuous time model I showed you? People discretize it, and then it turns out that if you wait a lot of time, and if you really adjust your noise, you will end up being in a global minimum. So in other words, this is the main idea behind simulated annealing, where you play with the temperature to drive the dynamics to a global minimum. So in other words, on the left, you see if you do something like simulated annealing, right? So which is, let's say, what the first model suggests is that you will wait forever, maybe e to the d iterations, but finally you will end up localizing in the global minimum, right? So that's what the first model was suggesting. Now, if remember, we replaced this model with something else, and then you can ask, what is the stationary distribution in your model, right? So it turns out that the stationary distribution has a characteristic, sort of has an explicit formula, and here's what we get. So it turns out that in this more jumpy model I have presented, the stationary distribution has support over all the local minima that you have. So for instance, here you have two local minima. So my stationary distribution has support over both points, but the probability of being in the wide valley will be larger. In other words, we have a formula for the probabilities as a function of the width of the valley. So if the valley is larger or is wider, you will end up picking higher probability. So what this says is that SGD will spend more time in valleys that are wider, and this behavior is going to kick polynomially fast in the dimension, as opposed to earlier models, which was able to guarantee this in exponential time. So then, I mean, sort of, we had this situation where we have some sort of heavy-tailed noise, but we don't know where it comes from. But we said, okay, we don't know where it comes from, but let's test it, right? So we said, okay, let's check it out and see kind of whether you have heavy tails. So in the paper, we have looked at different data sets, architectures, loss functions, mini batch size, etc. But so let me show you a few figures. So for instance, when we try this on the MNIST data set and the CIFAR10 data set, so these are classic benchmarks for kind of for simple deep learning problems. So what you see here is that on the y-axis, we estimate the alpha, the tail index. When it's 2, you have Gaussian behavior. If it's below 2, you have this heavy-tailed behavior I mentioned. So when we estimate, so there are some, based on the histogram of the data, you can really estimate these tails. So we have estimators that can tell you, how fast the tails are decaying. And based on this, in different settings, like different width and depth, we have seen that the tail index is a lot of times, away from 2, meaning that there's like a heavy tail behavior. And another thing we have observed is that, remember the ratio I mentioned, step size over bed size. So when we look at this ratio, step size over bed size, what we see is that if we increase it, meaning bigger step size, smaller bed size type of thing, what we see is that the tail index drops, meaning that you are heavier tailed. And then this leads to better generalization. So in other words, the experiments that we have suggest that, I mean, basically, if you are heavier tailed, then you have better generalization. And this has been kind of consistent in many different architectures. So one question you can say, okay, I mean, I don't know where this noise is coming from. I think shortly I will give you some explanation for why we end up having heavy tails. But for now, let's assume that there is some sort of heavy tail. So what can we do? I mean, one issue is that as optimizers, a lot of times stochastic optimization assumes finite variance. For instance, if you look at classic results by Polyak, Newrowski, Juditsky, etc., you have really nice optimality results, but they're often assuming finite second moment or finite variance in the iterations. So the question you can say, well, should we redo now the analysis with heavy tails? So it turns out that, I mean, you could adjust a lot of existing results to the heavy tail setting. So let me give you one example. So for instance, let's say if you have non-convex, suppose you have a non-convex objective. Here we just need local optimality, meaning that you want gradients to be small. If you, in classic theory with flight tails, like Gaussian type of noise, tells you that if you use a certain step size, you will have a decay in the norm of the gradients, right? So the question is, what happens if you have heavy tails? It turns out that now if you have heavy tails, now you are more jumpy, right? So then you have to use a smaller step size to be able to compensate for that. And it turns out that you have to use, what happens to your bonds? It turns out that you have to use a smaller step size to compensate for that, and your rate gets a bit slower. So for instance, instead of having skirt of k decay, now you will have cubic root of k decay, where k is the number of iterations. But the point is that a lot of the assumptions actually can be extended to this setting. And we also have a more general paper recently accepted in NeurIPS that looks into convex problems. Here, the result here is more on the non-convex setting. Okay, so basically we can do this. That's great. But at the same time, actually, when we were publishing this paper, actually, we were a bit worried because we were a bit worried that we may have made some mistake in the experiments. But luckily, when we posted, right after we posted our paper in the same conference, we realized that there was another paper by Martin and Mahoney where they have observed heavy tails in the weights, not in the gradients, but in the weights. So basically, and then basically they argued that so what they have seen was that initially you have like Gaussian like dynamics, but if you run the iterations, if you wait a bit, over time you run into this like heavy tailed regime. So basically they were saying that this well-trained networks can be modeled with heavy tailed weight matrices. So meaning that your weights admit so heavy tailed, the tail index, the weights, if you put them into a matrix and call them a weight matrix, the heavy tail models actually fit better to reality, if you wish. And the tail index was also sort of an indicator of generalization. So then more recently, we had another paper that sort of theoretically argues that this is in NeurIPS 2021. We have another paper that I'm not presenting today that also theoretically argues that heavy tails somehow should help with your generalization. And the idea here is that this sort of heavy tail behavior diminishes the effective dimension of the problem because of this sort of, because of this gradients being heavy tailed, you most likely you move in certain directions, and that helps reducing the effective dimension of the problem. But anyhow, there was this other works, and that also have seen something similar, and we were a bit like relieved. Okay, this heavy tail thing seems to be not a mistake. Our experiments are okay, and in different settings, in attention models, GANs, different structures, people have seen this heavy tail behavior. So the question, and one thing that actually another paper, Panigrai et al. Observed was that if the bet size is small, this heavy-tailed behavior is more evident. So in other words, if you use large bet sizes, you are more in the Gaussian region. Whereas if you use small bet sizes, you kick in this heavy-tailed behavior more often in practice. So then basically somehow there's a relationship between the step size, bet size, and the tails, but it wasn't clear to people what are the relationship exactly. But essentially the theory that we developed is a continuous time theory to study a discrete algorithm. We know these continuous time models are usually more user-friendly. So it kind of gives you some intuition that the ratio step size over bet size is a key quantity. It determines your tail index, and therefore it's correlated with the generalization. So that's the sort of argument we made in this particular paper. But the problem is that you can still ask, okay, where are these tails coming from? Like, why did they happen, right? So basically, this is the second part of the talk that I want to talk about. So essentially, the picture is like this. So you have generalization. For some empirical reason, we know heavy tails and generalization are linked. And this is kind of natural because, let's say, if you have heavy tails, this allows you to sort of, in your gradients, this allows you to explore better. And you can maybe think that this is the main reason for generalization. So now we know, for instance, generalization is linked to step size, bet size, and other things, right? But the question is, how are these factors, step size, bet size, and maybe Hessian, like the problem geometry, is affecting your tails? Like the question marks is not clear, right? How are the parameters affecting your tails, which is correlated with the generalization? So another question that we had was, why are these tails arising gradually over time, but not in the beginning? And another question you may ask, like, why is the small bet size creating a heavier tail in the gradients, right? So that's another question we can ask. And finally, you can say, well, do I really have to have a complicated predictive model to have heavy tails? What happens, let's say, if you are in the linear regression setting? Can you have these heavy-tailed sort of gradients? So, because the deep learning model is a complicated model, what we said, okay, let's study what happens in the linear regression setting and try to draw some insights to the practical deep learning setting. So it turns out that we have a complete theory for linear regression that tells you the exact relationship between step size, bet size, the Hessian of your problem, and the amount of tails you have. So basically, for the linear regression problems, we can complete the picture, and then I will show you that this sort of gives you some insights about the more general case. Okay. So the key is that basically, if you choose your parameters in the right fashion, even in linear regression, you can have heavy tail gradients. So that's the main message that I will pass about linear regression. So going back to linear regression, what's linear regression? I think there's a question. At the end of training, we often reduce the step size. Right. So yeah, I think there is a question by Daniel. So here I am assuming, so a lot of times right. So there is the train performance and the testing performance, right? So I think Daniel is absolutely right. Like, for instance, a lot of times for localizing the solution, we would reduce the step size. So in SGD, you could consider decaying step size, or you could also have a finite step size that is gradually decreased. Maybe step size equal to 1, a half, 1/4, etc. Right? So there are different step size regimes. And I think in the training setting, we kind of decay the step size. That makes sense. But what I'm talking about today is more on the constant step size regime, which also applies to more like this decaying step size regime, but we don't allow the step size going to 0. So in other words, so there, for training, smaller step size makes sense, but for generalization purposes, here I am. So here I'm arguing that the situation may be a bit different, and I'm only able to kind of cover constant step sizes here, but it would be definitely interesting to look at more decaying step sizes, right? But that being said, a lot of times also you could use a constant step size with a geometric kind of decay schedule. But maybe towards then I can tell you more about this. Thanks for the question. Okay, so if I want to go back to the linear regression problem, right? So this is a simple cost. Your model is linear, your cost is quadratic. So how does the iteration look like? Well, you will end up having something like a affine recursion, but it will be stochastic because of the stochasticity in the gradients. And if you write it down, what you see is that you have some, at every step, your SGD is multiplied with a random matrix MK, and it has obviously Hessian information HK in it, and sort of it becomes what we call a stochastic affine recursion. So, so this is a simple setting. So what we are after is we are trying to figure out what happens to our tail index when you run your algorithm, right? So so for simplicity of the talk, I'm going to assume we have Gaussian data, but in the paper actually we don't need this assumption. So for now, I'm assuming that the input data is nice and Gaussian. So what would you expect? Well, if the data is Gaussian, maybe everything will stay Gaussian, right? It turns out that that's not the case. So what we are after is we will argue that the tail actually has this polynomial decay instead of this exponential decay. So tails that decay slower than exponential are called heavy tails. And what we are after is that we are trying to figure out like how fast the tails decay in your iterates. So for instance, if the index is equal to 3, so if the alpha is equal to 3, what happens is that, let's say, your tail decays like 1/t cubed, right? So you have the faster decay in blue. If alpha is larger, it means that your tail is decaying slower. So it's like a kind of a characterization of how fast your tail decays, if you wish. So we want to compute this. It turns out that we have an explicit formula. Okay, so let me give you the formula. So remember, alpha is this index that I'm trying to compute. So if alpha is small, it means that I have heavy tails, right? Actually, heavier tails. Smaller alpha means you have slower decay and heavier tails. So it turns out that alpha solves this nonlinear equation you see in red here. So you see eta is your step size. I think there was a good question from Daniel previously. So this is not covering this decaying step size regime. You have the step size here needs to be bounded away from 0. So if you have the step size eta here, B is your bed size, and H is the Hessian, if you wish. It's like an estimate of the, you can think it as an estimate of the Hessian. So what you end up having is that this tail index alpha actually solves this equation. For instance, this HK comes from data, right? In particular, for Gaussian input, we can explicitly compute this. But basically, we have an explicit characterization of the tail index. How do we do this? Actually, we talked to queuing theory people in some operations research department. So it turns out that people, when they want to model systems, they use some sort of random models, and then using some existing kind of literature and adapting to our case, we were able to kind of show this. And the results can be extended to more general problems, but some of the explicitness of the characterization will go away. And what does this result tell you? Well, because we have an explicit characterization, we can study how the tail index depends on the parameters. In particular, we can see that if the bed size decreases, you become heavier tailed. Remember, a lot of times if you use a huge bed size, a lot of times people don't use very big bed sizes, right? And practically speaking, a lot of times people just stick to small bed sizes. So what we are saying is that smaller the bed size, you will invoke heavier tails, and consequently you will you will have a better generalization. You are likely to have a better generalization. So in other words, we can study the tail index and show some monotonicity properties. And in particular, we can also show that if you increase your step size, essentially you are building up more noise, and that's going to make you even heavier tailed. So if I want to kind of summarize these results, what's end up happening is that you have a critical threshold. So in typical stochastic approximation optimization literature, what people do is that let me choose a step size small enough. So because everything is small enough, I'm going to stay bounded. All my variance, etc., will stay bounded. Right? That's the typical. I also have worked in stochastic optimization, and that's the typical mindset I would have, and people would have in the in the field. So what happens if you use a larger step size than you are allowed to? It turns out that there's a critical step size. Here I'm giving an explicit formula. As you see, it depends on the bed size, dimension, and sigma square, which is like the sort of variance you have in your Hessian. So if you use a bigger step size than this, it turns out that you blow up the variance in your noise. In other words, the gradients or iterates have infinite variance at equilibrium. In other words, if you kind of exceed the step size, it's not that everything is killed. What happens is that your variance blows up, but you still converge to some distribution in the equilibrium. And as you can see, if I have a smaller bed size versus, so you can see that this critical step size depends on the dimension and different parameters. And people actually in practice have observed something similar. So there's a paper by Yasemin Bahri and Leikovich's et al. So a lot of times people say, if you use large step sizes in deep learning, as if you are almost going to explode, that can often work better. So in other words, people a lot of times try to pick large step sizes. So it's true that we a lot of times use a decaying step size, but a lot of times actually people, there are recent papers by this paper I put here and others that say that if you use big step size, a lot of times it can lead to better generalization. And we think what's really happening, we are speculating a bit, but probably what we think is that if the step size is larger, then this will kick in some sort of heavy tails in the gradients, which may lead to sort of better exploration and better generalization properties. So in other words, our results are sort of compatible with some of the existing kind of results that people have experimentally sort of observed. How much time do I have, if I may have? 10 minutes?
Yeah, so if we want to leave maybe 5 minutes for the questions, but it's up to you.
Okay, sure. Let me wrap this up. So then one can also study what happens to your moments. So basically, for a given step size, just take a linear regression problem, apply SGD to it. Okay, it turns out that depending on the step size, you have a tail. Tail index that we can give explicitly, and some of the moments will sort of blow up. Let's say if your tail index is 1.5, you know that the second moment will blow up. And in the paper, we can characterize how fast the moments grow. For instance, we can show that some of these moments blow up exponentially, but some of the moments blow up more like linearly, etc. So we have a finer characterization. And what's important is that so here we can also have a sort of a central limit theorem. So the classic stochastic approximation literature, like by Polyak, Judycki, Nemirovsky, etc., they kind of say that if you average the iterates, you will converge to a nice Gaussian distribution, right? So this is classic kind of optimality for in stochastic sort of optimization algorithms. But here, it turns out that with the step size that we are choosing, right, it's large enough so that the average of the iterates will not be Gaussian, but it will be this more general heavy-tailed random variable. So we have some sort of we can also kind of redrive the sort of the existing theory more from a different angle. So basically, the classical theory wouldn't apply, but the limit would not be Gaussian in our case. And just to, in the last 3 minutes I have, maybe just let me give you some experiments. So we tested out what I mentioned on synthetic linear regression. So we kind of saw, okay, if you, everything I talked to you about, like if you fix the step size and increase the bed size, you see more like a Gaussian behavior where tail index 2 means you are Gaussian, right? Where if you fix the bed size and increase the step size, you see that the tails are getting heavier. The same thing, basically the ratio it over bed size, step size over bed size, also if you increase that ratio, you also get heavier tails. And then one thing we did was there's also this variance reduction methods where they are based on reducing the gradient. So for instance, we looked at our RMS prop here. And in this variance reduction methods, because they are killing the noise in the gradients, you end up getting essentially a Gaussian behavior. So that's also interesting. So basically this behavior of SGD in variance reduction methods, you don't see them. So when we tried like a simple thing like CFAR10 on different layers, we also, so each layer, so we look at layer-wise, we estimate layer-wise tail index. And we have seen that this, as I mentioned in the previous slide on synthetic data, you have this inverse relationship between this step size to bed size ratio. So if you increase it, then the tails become heavier. And then we, one of the referees said, okay, this is great, but how about bigger networks? So then we kind of tried VGG 19. And then here for every layer, we also observe the structure. So basically the step size over bed size ratio, if you increase it, then you get more like sort of heavier tailed sort of tailed performance. So in other words, the ratio that, the theory that we have is for sort of linear regression, but also we have seen that that's sort of somehow useful in deep learning practice. Okay, so if I think I'm not going to have time about this, but then the question you can ask, okay, if it's really great to have heavy tails, so the problem is that they are sort of occurring towards the end of training, right? In the beginning, you have Gaussian noise, but over time, it becomes like a sort of heavy tail. So then we thought, okay, how about we invoke heavy tails right from the beginning, rather than waiting? So typical initializations actually would have something like a Gaussian initialization, so that in the first iterate, because you initialize with Gaussian distributions, you initialize your weights with a Gaussian. Essentially, your gradient is not heavy tailed, right? But the heavy tail kicks in over time. Here we tried something else. We said, okay, let's kind of choose an initialization in a particular way so that it will kick in heavy tails from the beginning. So when we did this, actually, we also had a bit of improvement on CFAR10 and MNIST and a few other data sets in the training. So if I just want to summarize, there's this basically this phenomenon in the gradients that we see, unlike so for some reason in deep learning, there's this heavy tailedness in the gradients that we want to understand better. Right now, the theory is a bit limited. Our theory is limited to linear regression. But we could generalize it to some other models like logistic regression and so forth. But it would be nice to have more theory in this direction. And also, I think there are problems about, for instance, here I was assuming that, so there are other problems for instance, here I was assuming that the data is coming in an online fashion, but actually in practical SGD, typically you do it offline. So there are a lot of things to figure out, but we think that sort of this sort of understanding SGD and its generalization properties is really important, to have better algorithms in deep learning. And here we can characterize exactly what is the dependence of the tail index to the parameters so that we can explain why sort of certain parameter choices lead to better performance, and we can also leverage this to have better algorithms. With that, thanks very much for listening, and I'm happy to take questions.
Awesome. So thank you, Mert, for the presentation. Very, very informative. A lot of new things. So yeah, so the way we're going to do is you can raise your hand if you have a question to ask, or you can just type it on the Q&A or the chat, and then we can move from there. So yeah, raise your hand if you have any specific question. And so while we wait for the audience, maybe I have one about the stationary distribution of the Levy process. Right? So you mentioned that there is this probability distribution whose support is the local minima, with higher probability on wider local minima. But then here, is this a limit taken? So does it mean that the SGD process converges to a point process between the local minima, or is across multiple runs of the SGD or different samples? Where is the limit taken over?
Right. So that's a great question. So let's say in the classical simulated annealing case, right, you would let the noise going to 0, right? You have a coefficient in front of noise and you let it go to 0, right? So here you can think this way. So if for every, let's say you have this heavy tail noise and you have a coefficient in front of it, let's say epsilon, right? For every epsilon, you have like a limiting distribution.
Okay.
So then you can ask, okay, what happens if I choose a small epsilon? It turns out that in the limit, it converges to that limiting distribution, where you only jump from local minima to local minima.
Right. So it's okay.
But for small epsilon, you actually see not Dirac's, but something like around them. Yeah, but a good question. So it depends on how you take the limits. Yeah.
Right. And I guess this is only enabled because you can have jumps, right?
Right. So exactly. So what happens is that when you, let's say, run SGD in deep learning, a lot of times you see the cost comes like this and then jumps, and then comes like this and jumps. So then the question is, if you want to have a continuous time model, do you want to allow jumps or not, right? So that's the question. And what we argue is that if you don't allow jumps, then you have to climb over a big height. It's like coin tossing. You have random noise, and then you are kind of rowing against the current, so you need a lot of time to cross over. So allowing jumps allows you to have like a quicker kind of transition. Actually, it's polynomial time between the local minimum instead of exponential.
Okay, but you're not breaking any lower bound, right?
No, that's true. I'm not breaking any lower bound because it's like this Heisenberg type of thing. So I'm converging very fast, but it's not localized. Right. So if you want to locate the global, you need exponentially many. But what I'm doing is I'm going some very fast, but I'm not figuring out the exact global. I'm figuring out only local.
Okay.
But that's a good question. Yeah.
Okay. Thank you. Yeah. Is there any more questions from the audience? No. Or maybe I can ask another one, which is about tools. So when a lot of tools are available for Langevin dynamics,
right.
Do we have the similar set of tools for Levy processes? So
it's a bit less developed, to be honest, because people were more interested in the Langevin stuff. But we have some, and we can use some of those. But some of them we had to drive on our own. But it's surprisingly, statistical physics people worked on this. So it's like some statisticians luckily worked on it. So we have some tool sets, but one problem is that, let's say in the Langevin, as you know the limit distribution explicitly, regardless of your step size, right? It's like the e to the minus thing, like the Gibbs distribution. So here in Levy thing, you only know it if you let noise go to 0. So otherwise, you don't have an explicit expression. So that makes thing a bit like harder.
Right. Yeah. So some people in optimal control also study like these stochastic partial differential equations with jumps and all that. Yeah.
Right. I think in control it's very common. Yeah.
Okay, so I'll ask one more time. If there is any questions, you can raise your hand. Okay, if not, then so let's thank Mert again. Thank you for joining us today, and yeah, this was very exciting. I hope you can visit us in person soon as well.
Definitely, it would be very nice to have you as well. Thank you very much again for the invitation.
Thank you, Mert. Bye. So I'll just stop recording and I'll